everyone, and welcome to CRAMSURG, Clinical Research Appraisal and Methodology for Surgical Trainees, where we pick a paper fresh from the press on a hot general surgical topic. We review it for you, we present it for you, we critique its methodology for you, and provide top-of-the-field expert opinion and teaching on research appraisal and methodology. My name is Gio Perrin, and together with Professor Sababala Subramanian and Maria Digby, we bring you CRAMSURG from the wonderful region of the Yorkshire and the Humber.
Welcome back, everyone. Today we'll have a look at a paper on the neoadjuvant treatment for locally advanced rectal cancer, comparing chemotherapy and chemoradiotherapy. A very important, hotly debated topic, so stay tuned for that. I will be delivering a short talk on non-parametric tests, outliers, and Wilcoxon. Following that, hopefully you'll find that interesting. I'll leave you to it.
Good evening, everyone. I'm Constantine, and I'll be presenting this with Obafemi, who is an STC in Sheffield at the moment. The paper we're reviewing today is titled Neoadjuvant Chemotherapy versus Chemoradiation for Locally Advanced Rectal Cancer. This is a multi-center propensity score-matched study by Diaho et al. And published in Disease of the Rectum, Colon and Rectum in the December 2025 edition. This paper is of interest because they looked at an evolving area in colorectal surgery and presented a result that might be of interest to colorectal surgeons and everyone interested in rectal cancer. As a background, the authors highlighted that the current conventional chemoradiation used as neoadjuvant therapy for locally advanced, though has clear benefits in reducing local recurrence, the overall survival and the benefits with regards to distance metastasis is doubtful. And when you compare this to the toxicity of radiation, which impacts the quality of life, experts in this field began to look at other ways of looking at the treatment, neoadjuvant treatment for locally advanced rectal cancer. And they pointed to PRODIGE study, Rapido, and Prospect study, which added neoadjuvant chemotherapy to the conventional therapy and found some beneficial effects. The authors in their previous paper also noted that using neoadjuvant chemotherapy for rectal tumors that have not evaded the mesorectal fascia had some benefits. And with current advancement in imaging that could clearly delineate the involvement of cancer with the mesorectal fascia, those with low risk could be identified. And these were the rationale they presented for this paper. I'll hand over to Femi to discuss the objective and the method of the study.
All right, next slide. The authors looked to compare survival outcomes, such as disease-free survival, overall survival, and metastasis-free survival between neoadjuvant chemotherapy and neoadjuvant chemoradiotherapy in patients with locally advanced rectal cancer. The population study, the PICO, the population reviewed in their retrospective cohort analysis was involved patients with clinically staged locally advanced rectal cancer with at least T3A to B, N0 to 1, M0 for local rectal tumors, or T3A to C, or T4A, N0 to 1, M0 for middle to high rectal tumors. And this was defined as tumors that were at least 5 centimeters above the anal veg, without involving mesorectal fascia. And these were collected across two major cancer centers in the western parts of China between 2015 and 2021. The intervention was neoadjuvant chemotherapy, which was oxaliplatin based. It was either Capox, capecitabine and oxaliplatin, or Folfox, 5-fluorouracil, leucovorin, and oxaliplatin, administered at least 2 months before total mesorectal excision. That was compared to the standard therapy, which is neoadjuvant chemoradiotherapy, 50.4 gray in 25 to 28 fractions, with concurrent use of oral capecitabine, followed by TME surgery, 8 to 12 weeks post-treatment. The outcomes reviewed were primarily for disease-free survival, and then other secondary outcomes such as overall survival, metastasis-free survival, and local recurrence rates. These endpoints assess both oncologic control and systemic efficacy. The study design was a retrospective multicenter cohort study using propensity score matching to compare neoadjuvant chemotherapy and chemoradiotherapy for locally advanced rectal cancer. The patients included, as I mentioned before, were locally advanced rectal tumor in those specific stage, T3A to B, N0 to 1, M0 low rectal, and T3A to C, T4A, N0 to 1, M0 middle to high rectal cancers without mesorectal facial involvement. They excluded patients who had had previous chemotherapy, patients who had had other cancers who were having treatments, patients who had lost records, and a few other exclusions. And the presence of metastasis, presence of breaching of the mesorectal fascia was also an exclusion criteria. The treatment protocol was neoadjuvant chemotherapy was given, an oxaliplatin-based therapy was given for at least 2 months, and the chemoradiotherapy group had 50.4 gray radiation in multiple fractions with concurrent capecitabine. All patients underwent total mesorectal excision performed by expert colorectal surgeons. The follow-up involved regular assessments, including CEA and CA19-9, and chest, abdomen, and pelvic CT scan every 6 months for 3 years, then annually afterwards. The last follow-up was completed in January of 2024. The statistical analysis involved the propensity score matching was used to adjust for baseline differences between the neoadjuvant chemotherapy group and the chemorad group, using 1-to-1 greedy nearest neighbor matching with a 0.05 caliper. Survival analysis technique used was the Kaplan-Meier curves to estimate overall survival, disease-free survival, and metastasis-free survival. Cox proportional hazard models calculated hazard ratio with 95% confidence interval. The results will be presented by Constantine.
Thank you very much, Femi. Over the study period, as we can see, the two centers are actually high volume because they saw a total of 1,001 patients, and those with low rectal cancer were 544. After exclusion, those that received neoadjuvant chemotherapy were 205, and 159 received chemoradiotherapy, which appears to me that these centers are evolving to giving their patient neoadjuvant chemotherapy before surgery. After the propensity matching, They were able to match 118 in both arms, and the analysis was done for this 118 in both arms and also for unmatched group. So they compared the outcome in both groups after propensity matching and before. The baseline characteristics of the patient, those that received the neoadjuvant chemotherapy had higher BMI, lower rectal cancer. The NO staging were more in them, and it's worth noting that they had lower extramural vascular invasion. After propensity matching, both groups were said to be matched in sex, age, BMI, tumor location, and clinical stage and extramural vascular invasion. The demographics of the patient were similar before matching, and T3B tumors were more in those that had chemoradiotherapy, but after propensity matching, they were similar. Looking at the primary objective, which is the overall survival, disease-free survival, and metastasis survival, the results they presented showed that those that had the neoadjuvant chemotherapy had better overall survival with hazard ratio of 0.31. And the result on the chart is before the propensity matching. And before this, the neoadjuvant chemotherapy showed better results for both overall survival, disease-free survival, and metastasis-free survival. However, for metastasis-free survival, this was not statistically significant. The hazard ratio for this was 0.62, which could be interpreted to mean that about 38% reduction in metastasis was seen in those who received the neoadjuvant chemotherapy. And when the propensity matching was done, the results on the graphs shows better outcome for better overall survival, better overall disease-free survival, and metastasis-free survival for those that had the neoadjuvant chemotherapy. The hazard ratio for metastasis-free survival was 0.47, and we could interpret this to mean that receiving neoadjuvant chemotherapy reduced the hazard of metastasis by 53%, and that applies to overall free survival, which with hazard ratio of 0.36 and disease-free survival of with hazard ratio of 0.51. Looking at the surgical outcome, those in the NCT group had less stoma, and this is statistically significant. If we look at the result, 54% of them had stoma to prevent anastomotic leak, while those in the chemoradiotherapy, about 80% of them had stoma. The operating time was noted to be shorter in those in the group that received the neoadjuvant chemotherapy. This was also statistically significant. Similarly, blood loss and hospital stay were lower in the neoadjuvant chemotherapy group. The quality of resection was similar in both arms of the study. Looking at the pathological outcome and the tumor resection, the efficacy of neoadjuvant chemotherapy and chemoradiation were similar in both groups. And similarly, in downstaging, the outcome was similar in both groups. And the resection margin was 100% in both groups, which this means that both the neoadjuvant chemotherapy and the radiotherapy had somewhat similar impact statistically, looking at tumor reduction or downstaging before the surgery. The key takeaway from these results shows that the group with neoadjuvant chemotherapy had better metastasis-free survival compared to those with chemoradiotherapy, and there's comparable pathological efficacy in both arms of the study. However, this needs to be tested in better studies like randomized control trials. The limitations that we picked out of this study, I think they were all reported by the authors. The retrospective nature of the design, which is prone to selection bias, though the authors had a propensity score matching, this could not totally remove the selection bias. This study had moderate sample size, so there is need to interpret the result from this with a pinch of salt. And then the heterogeneity in the neoadjuvant chemotherapy that was administered is also a limitation in the study. I would hand over to Femi to discuss or conclude this presentation.
Yeah, in conclusion, the authors surmise that neoadjuvant chemotherapy appears to be safe, is associated with better survival outcomes compared with neoadjuvant chemoradiotherapy for patients who were so staged with low rectal cancer. We reviewed the paper and felt it was good that they tried to approach the population studied using the propensity score matching in order to eliminate bias in this study. They used the appropriate statistical tools in the setting of the data available, but because it's a retrospective designed study, it's probably not easily transferable. It's also a paper that addressed the clinical question they were asking. We felt that it addressed the clinical question, which was to assess disease-free survival and which intervention was better. However, there was no point in their whole paper where they mentioned toxicity profile. There was no talk about the possible complications or the effect of either treatment arm. Thank you.
As usual, a few points that we discussed after the paper presentation. The first point we wanted to make relates to the reasons behind choosing one treatment approach, that is to say, chemotherapy or chemoradiotherapy for the patients included in this study. It is rather unclear how patients were selected for one treatment or the other. It is important to highlight that the two treatments are rather different. Chemoradiotherapy is basically radiotherapy with capecitabine, which is a relatively well-tolerated oral chemotherapeutic agent. Chemotherapy is a rather heavier oxaliplatin-based course of treatment. It does have significant side effects and toxicity. We do think that does have a significant impact on the patients that are then followed up. Because, as you probably noticed, patients that did not complete either of the courses were not included in the analysis. And it is reasonable to assume that a lot more patients would not complete or tolerate a complete course of chemotherapy, given its side effects, rather than chemoradiotherapy. This is an assumption, but it is reasonable to think so. This has two implications. The first one is that the two groups might well not be comparable. And the second one is that the group that does complete indeed chemotherapy would be a stronger group, a group that was able to cope with such side effects. Hence, they would have a natural survival advantage over patients that perhaps were at the baseline less fit. You can kind of see that in the survival curve that the authors present. And if you look at it, you'll notice that the first part of the survival curve for chemotherapy is rather flat. And this indicates that perhaps there is an element of immortal time bias. We also had a quick chat about the propensity score matching that they performed. As much as they take into account a number of pre-treatment variables, it is important to highlight that comorbidities were not really included. Hence, it is difficult to say whether those were somewhat made more homogeneous in the two groups by the propensity score matching system. Right, I'll leave you to the teaching session. Enjoy.
Today we're going to briefly talk about outliers and Frank Wilcoxon, that is to say, one of the fathers of non-parametric tests. Usual disclaimers: I'm not a statistician or an expert in statistical software, but I often like to play with stat software and statistics. Brief look at what we have done so far. We talked about assumptions. We talked about now a significant number of statistical tests, some of them suitable for normal distribution, some of them not. Particularly, we talked about how Spearman's and Kendall's correlations particularly are very useful when the data is not normally distributed. And we looked at how to run them. So today we're going to move on a little bit, and we're going to talk specifically about skewed data. And we are going to talk about what happens when you are comparing two groups with continuous numerical data, when the numerical data is either paired or non-paired. And to start with the example, we're going to start with non-paired data. We're going to look at it using Jamovi. So let's start our story, which is probably the most interesting part of this presentation. So Frank Wilcoxon was a chemist, and he was doing some experiments back in the days in his lab, and he managed to get his hands on a particularly famous book at the time, which was Fisher's book on how to conduct a scientific experiment. That sort of very famous book that we talked about, that introduced the concepts of randomization, etc., etc. And he realized that a lot of the things that were written on that book were actually not working very well for him, because he was dealing with an environment where things were not sort of always happening in a fairly controllable way. Whenever you're dealing with a chemical reaction, you've got lots of things that can change the way a particular reactant interacts with an enzyme, and the speed by which the reaction happens can be affected by gajillions of variables. Most noticeable: temperature, presence of catalysts, contact between the elements, concentrations, pressure, and so on and so forth. Conditions that are very, very different from a crop, which is where most of the statistics that Wilcoxon were dealing with actually originated from. If you remember, for example, student T was coming from studies on crops. A lot of the early studies that were published by Fisher were also on crops. So a very, very different environment. And he couldn't quite work out why what he was trying, the statistics he was trying to use on the experiments he was running, were not working. So he very quickly realized that he had two problems. One problem was outliers. Whenever he was doing a reaction, he would do perhaps 3 or 4, 5 of these reactions with the same amount of chemical A, a same amount of substance B, and obtain very, very different levels of substance C. Or he was obtaining substance C at very different speeds, to the point that some of the results that he had were completely off the chart. And he couldn't quite work out why, and he couldn't quite work out why this was affecting the statistical test he was running. To determine differences between these samples why it was affecting them so much. And he pretty quickly realized that some of those results, that is to say outliers, were significantly affecting his calculations. That's one of the main problems he had. The second problem he had was the distribution. So the vast majority of what was published at that point was based on a normal distribution, and he certainly had a very abnormal distribution. Paranormal, this vignette would suggest. So he set off to resolve this problem. And the first problem he had was, well, what's an outlier? Difficult to say. Interestingly, there is no universally sort of recognized definition of an outlier. This is Stephen Hawking's definition of an outlier, which, as you can see, is very generic. You could apply it to pretty much anything, from chemistry to crops to boyfriends, as you can see in this lovely vignette. By the way, if you're interested in where these vignettes come from, it's a lovely website. You can snap the QR code on the bottom left. It's really funny if you like these type of things. So let's go back to our previous vignette, outliers. No clear-cut definition, but there is a way to kind of define them, or at least visualize them, and that is to say the box plot. Box plots have been around for bonkers years, and they're still very underutilized in data representation, both in medicine and outside medicine. The vast majority of box plots and the softwares that do make box plots, including Jamovi, will flag up when a distribution is affected by outliers. And the definition of outlier in the classic representation of a box plot is anything, and you have to follow me for a second here, that lies 1.5 of the interquantile range above or below, respectively, the third or the first quartile. I hope that makes some sort of sense. So if you look at this box plot, for example, we could see that this kind of contains a graphical representation of sample. This is the third quartile. This is the first quartile. This is the median. This is the max. This is the min. So if there were to be data that sits more than 1.5 times above this point in comparison to this block, it will be flagged up as an outlier. You can see it here because these 2 points lie well above 1.5 of these. Okay? I hope it makes sense. Feel free to interrupt me if it doesn't. And that's a very simple way to figure out whether your distribution, the data you're analyzing, has got outliers or not. Outliers and the tendency of a distribution to have outliers is sort of defined as kurtosis, which is another way of determining whether your data is prone to have outliers. And kurtosis has to do with how spread out the tails of your distribution are. Okay. This terminology, I must say, I've never actually seen it used in common jargon, but basically, this is a flat, this is an average, and this is a very tall, with relatively limited tails distributions. Remember that it doesn't matter how tall this is, it's the tails that make the difference, okay? Kurtosis can be calculated, and this is normally said to be above 3, and this is said to be below -3, I seem to remember. Or we'll have a look at it in the software in a minute. Obviously, normal distribution, which is, again, the most important concept here. And this was the other one of the problems that Wilcoxon was facing. So one was crazy outliers, and we kind of talked about how you pick them up. And the second one was a normal distribution. His distribution was very abnormal. And how did he get around it? Well, very similarly to what Spearman did in his rank correlation. So he designed a test to compare 2 groups of continuous variables. Instead of using the actual value, he would use the rank that value take in the distribution. And this is just an example, the same that we used a few weeks back. We have a number of plants. Each plant has a certain height, and each plant produces a certain number of grams of marijuana. That is to say, no clue if this is actually in any shape or form accurate for real life, but anyway. So as you can see, the numbers are very different. So this is 45 centimeter, most certainly would be an outlier. And you can see if you were to plot it in a normal plot, having plant height on one side and produce gram on the other side, you would probably get a crazy intersection point here. So in order to kind of make the data sort of more digestible to a statistical test, instead of using these absolute numbers, you can use the rank. And in this particular case, 25 centimeter will be rank 2 because it's the second value from the bottom. 23 centimeter is rank 1. 27 centimeter is rank 3. 45 centimeter is rank 4. The same goes for the grams. So you can see that because this is the biggest number of grams, and this is the highest value you get on the plant, they both rank 4. And if you think about it, you can imagine how ranking variables kind of transforms your distribution into something that's a bit more normal or a bit more handleable, if that makes sense, especially if you're dealing with massive numbers. Like think about comparing, I don't know, the populations of different countries, United States versus UK. Obviously, the United States is massive. If you put all the countries of the world, you'll have a few that are at the top with millions and billions of population, and the vast majority will be in the middle, so those will be outliers. If you rank them, instead of using the absolute number of people that live in there, you will probably get a more sort of accurate representation of the statistical relationships between various countries, if that makes sense. Just a quick note, the Wilcoxon rank sum test, which is sort of what we discussed so far, is also called Mann-Whitney-U, and it does deal with independent samples. So 2 different populations with 2 different sets of variables. The Wilcoxon signed rank test, on the other hand, is the equivalent for non-parametric of the paired students T. So it deals with paired sample, where you have a measurement taken at time 0, an intervention and measurement taken at time 1, such as blood pressure pre and post treatment. I hope that makes some sort of sense. So to give you a practical example, we'll go back to my dissertation data set, which we've used now pretty much in every session. If you recall, for this particular study, I collected data about papers that were advertised on Twitter by publishing journals. And today we're going to look at retweets data, and we're going to try and determine whether there's a difference between medical and surgical papers in terms of number of retweets that the papers get. So let's have a quick go. Unless you guys have any questions before I fire up Jamovi.
So, quick question, Gio.
Yeah.
So the Wilcoxon's rank sum test
Yes.
is the same as Mann-Whitney? I hadn't realized that before.
Yes.
And it's different to the Wilcoxon's signed rank test because obviously that's for paired data, yeah?
Yes, correct.
Okay. Thank you.
In Jamovi, let's start by doing a bit of box plotting, because I think Jamovi does it really well and does it very quickly. So the problem I found when I was looking at generating box plots in this data set is that the values I've got are very significantly affected by outliers. So it's nearly impossible to find a decent looking box plot. They all look like this. Let's have a look at this one, for example. Yeah, a bit better. So you can see how this box is the interquartile range. The median is in there. And you can see how everything
that's 1.5 of this above it is flagged as an outlier. Also, Jamovi is quite smart, and obviously the density of this plot is massive, but it does flag you what row in your data set the outlier is. So you can go and find it if you want to, and explore why it is an outlier. So it is very, 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 very easy to do box plots in Jamovi. Don't try and do them in Excel, it's a mess. See if we can get one, that's nice. No, they're all pretty much the same. That's because my data is very abnormally distributed and it's got a lot of outliers. It's just the way the data is. You can take the labels off if you want. And it does also tons of other plots if you want to, but today, for the purposes of defining outliers, we're gonna stick to that. Now, let's move on to the Wilcoxon test. Unfortunately, it is labeled under t-test for whatever reason. You have to go onto independent samples t-test. And we said we were going to look at retweets, so let's do that. Don't worry about the extra bits on the label. It's something I've generated some time ago. And we split it by grouping variable. And as you would expect, the first thing it does, it gives you a student's t-test. It also tells you that the variances are different. But here you can find the Mann-Whitney U-test. Can remove the student's t. So it's very easy to run it here in Jamovi. And you can then also run additional statistics. Very importantly, normality test. We explored this last time, a few sessions ago. This data is not normally distributed, and Jamovi tells you quite quickly. You just have to check normality test. It also gives you an homogeneity test. If you remember, we talked about this, the Levens test. So the variances between the two groups are very different. That's it. Not much else to add.
Thank you everyone for tuning in and listening. Until next time, keep running your life with our surgical work.